Well, I think it's time. So I'd like to start by saying Toda Rabba to the organizers for asking me to chair this session. And welcome to the either afternoon or morning session of FPSAC 2021, depending upon where in the world you are. Our first speaker is my colleague and co-author, John Shareshian, who's going to be talking about Hessenberg varieties and combinatorics. Two great things. So, John, take it away.
Thanks very much, Bruce, for the introduction. It's always great to see you. And let me begin by thanking everyone involved in organizing this. I know this conference is a very large enterprise. A lot of people put in a lot of work, and I want to thank all of them. And I want to thank the local organizers in particular who have labored tremendously under very tough conditions to bring off something like this. And I'm just sorry I can't thank you in person, but it's a pleasure and an honor to get to talk here. I'm going to discuss, for the most part, older work with my most frequent collaborator and longtime friend, Michelle Wax. If time permits, I'll discuss some newer work with my new friends and current colleagues, Laura Escobar and Martha Prekup. So let me start by telling you what's a Hessenberg variety. Okay, so a Hessenberg variety is defined using two ingredients, the first of which is a Hessenberg vector. And this is just a weakly increasing sequence of integers satisfying the condition in integers for some fixed but arbitrary positive n. I have n integers written in weakly increasing order. All of them are at most n, and the jth integer is at least j. So just for fun, here's a Hessenberg vector. Right, there are 6 integers, they're all at most 6, and the third integer, for instance, is at least 3. Okay. Well, that's half of what we need to define a Hessenberg variety. The other half is a matrix, an n by n matrix. And given a Hessenberg vector and an n by n matrix, you can define a subvariety of the flag variety. So the set of all full flags in complex n space is a projective variety. And we're going to impose some algebraic conditions depending on the matrix X and the vector M that cut out a subvariety of the flag variety. Right? And so given a flag, we check whether when we apply this linear transformation X to the jth subspace, we end up inside the mjth subspace. So mj is at least j, so this is at least feasible, even if X is non-singular, right? The dimensions are okay, right? And so we check if for every j, when I apply X to the jth subspace, it's inside the mjth subspace. That's an algebraic condition. And so the set of all flags satisfying this condition here for every j is a subvariety of the full flag variety. I'd like to work through an example with you just to make clear what's going on. All right, so here's my matrix X. It's diagonal, and it doesn't really matter what these eigenvalues are. The key point is that they're distinct for this particular example. So I have a diagonal matrix with 3 distinct eigenvalues. I have a Hessenberg vector of length 3. And now what's the only non-vacuous condition? The only non-vacuous condition is that when I apply X to the first space in my flag, it's contained in the second space, right? Because this 3 here just says I have some flag. It includes a 1-dimensional space and a 2-dimensional space. This 3 here just says if I apply X to the 2-dimensional space, it's contained in C3, which is vacuous. Of course, this condition imposed by this 3 is also vacuous. So this is the only condition, right, that we have to worry about. So I'm looking at all flags, a 1 space and a 2 space in C3, such that when I apply this matrix X to the 1 space, I stay inside the 2 space. Okay, so I'd like to just draw a schematic. This case, we can just handle kind of barehanded and understand, right? So here's the Hessenberg variety. Right, and here is P2. set of all, the variety of all one-dimensional subspaces of C3, right? And what I'm going to do is take some flag called V bullet. So this has V1 and V2 in it, and I'm going to map it down to V1. All right, so this is some nice map from our Hessenberg variety, the variety of all one-dimensional subspaces of C3, right? I just temporarily ignore V2. And now I'm going to ask what the preimage of some space down here. This is close to an isomorphism. Well, let's look where it's not an isomorphism, right? Say I take an eigenspace. I look at a standard basis vector, I look at its span, that's an eigenspace, and these are all the eigenspaces, so there are 3 of them. And I ask, what's the preimage of this? Well, since this here is an eigenspace, this condition is again vacuous. We know V1's inside V2, and XV1 is just V1. So I can pick any V2 that contains my particular one space here, and I'm going to get a legal flag, right? Well, the set of all 2 spaces containing a fixed 1 space is the same as the set of all 1 spaces in the quotient by that 1 space. And so living above one of these eigenspaces is a P1. Right? But if I take some other one-dimensional space, let's just call it Z, that's not an eigenspace, well then, right, Z has to be contained in V2, and so does XZ. And since Z and XZ are distinct, V2 has no choice but to be Z plus XZ. Right? So here, right, we just have the flag Z is less than Z plus XZ, and that's the only preimage. All right, so basically away from these 3 points, right, this variety here just looks like P2. Above these 3 points, right, you have a P1. And so what you see is this particular Hessenberg variety here looks like P2 with 3 points blown up to P1. And just for future reference, we can compute the non-zero Betti numbers, right? The first cohomology group is 1-dimensional, or is the 0th source. The second is 4-dimensional. One of them comes from the P2 and the other 3 come from these 3 P1s. Right, and since this is combinatorics, you might notice that these are the coefficients of the Eulerian polynomial for S3. Okay, so that's what Hessenberg varieties look like. And now here's my plan. I am going to go through some old work with Michelle, right? I hope it's new to enough of you that I'm not wasting your time, about the relation between regular semi-simple Hessenberg varieties. So regular semi-simple just means that the matrix X looks like the one we just looked at. It's diagonalizable with indistinct eigenvalues, and a conjecture of Richard Stanley and John Stembridge about chromatic symmetric functions. If time permits, and my practice talk indicates that's going to be a close call, I'll discuss some newer work with Laura and Martha about relations between Hessenberg and Schubert varieties, and Hessenberg also some facts about Hessenberg varieties of codimension 1, the flag variety. But I want to start here, and this requires a digression away from Hessenberg varieties to discuss chromatic symmetric functions. Right. So I have a finite graph. It's got a vertex set and an edge set. Right. And what this chromatic symmetric function, this was introduced by Richard Stanley in the 1990s. This chromatic symmetric function is just a generating function for all proper colorings of this graph with positive integers. Right. So I have a set, infinitely many pairwise commuting variables, and this set of all proper colorings. That just means I assign a positive integer to each vertex in such a way that 2 vertices connected by an edge get different colors. Associated to each such coloring is a monomial that just tells me how many times each variable is used. I add up all those monomials, I get the chromatic symmetric function. So let me show you by example how this looks. Right, so I take this graph here, and now I'm going to assign a positive integer to each vertex. So for instance, right, in such a way that 2 vertices joined by an edge get different colors. So this is a perfectly legal coloring. I used a 5 here and here, but they aren't joined by an edge. This 11 is different than these two 5s. This gives me a monomial x5 squared x11. Right. The other kind of thing I could do is just use 3 different colors. Like this, I assign color 3 here, 7 here, 6 here. I get the square free monomial x3, x6, x7. Right, and these are the only kind of legal colorings there are. And the key point is it doesn't really matter what colors I use. It matters, right, how they are related to each other with respect to the edges. Right, and so here the chromatic symmetric function is, well, I'll write it this way, 6m11 plus m21. What does that mean? I hope most of you are familiar with symmetric functions. I'll try and run through quickly for those of you who aren't. M111 is the sum of all square-free monomials of degree 3 in these infinite variables. And the reason I see 6 M111s is if I'm using 3 different colors, I can permute them any way I like, right? I could have written 367 or 736 or so on here. I still have a legal coloring, and it doesn't matter which 3 variables I use. I'm going to get 6 legal colorings using those variables. M21 is the sum of all monomials of the form xi squared. One of the exponents is 2, xj, the other is 1. And there's only, right, given a I, which I'm going to see 2 I's and a J, this is the only way to do it, right? So I see this is a symmetric function. It's in fact, a homogeneous power series whose degree is the number of vertices, which is invariant under permutation of the variables, right? So this is the chromatic symmetric function. Since Stanley introduced these, there's been a lot of attention paid to these. The idea is, well, it contains, in fact, more information than the chromatic polynomial about colorings, and you can hope, right, to learn something about the relation between the structure of the graph and the expression of this symmetric function in terms of the various familiar bases for the space of symmetric functions. Okay, so this is an industry. There are many interesting things involved, but we want to relate them back to Hessenberg varieties. This is the goal. Okay, so let's go back. Remember, we have one of these Hessenberg vectors, and what we're going to do is create a graph whose vertex set is the numbers 1 through n, right? And what edges we're going to have? We're going to have the edges ij such that I is less than j, but j is at most the ith entry in our Hessenberg vector. So let's look at this one. We have vertices 1 through 6. Right, and so M1 is 3, which means that 1 is connected with 2 and 3. M2 is 3, 2 is connected with 3, right? M3 is 5, M4 is 5, and M5 is 6, right? So this graph contains exactly the same information as this vector. So given these Hessenberg vectors, at least, we get graphs, right? So this is half the information needed to construct a Hessenberg variety. And now let me, this is my language, call this the weak Stanley-Stembridge conjecture. The Stanley-Stembridge conjecture, I don't want to make all the definitions, says that the incomparability graph of a 3 plus 1 free poset has E positive chromatic symmetric function. The chromatic symmetric functions of certain graphs can be written as non-negative integer combinations of elementary symmetric functions. These GMs are a special case, right? These GMs are in fact incomparability graphs of posets that are 3 plus 1 free and 2 plus 2 free, but it's a theorem of Mathieu Gay-Paquet that if you prove this weak Stanley-Stembridge conjecture, the entire Stanley-Stembridge conjecture follows. Now, if you're not in algebraic combinatorics, maybe this looks like a kind of specialized and unmotivated conjecture, but this is actually very, very interesting. It arises from an earlier conjecture of Stembridge about immanence of Jacobi-Trudi matrices. And sorry, I'm going to leave the lights off. If I don't move, they're going to stay off. right? This has spurred a lot of interesting work. So it might look specialized, but it's not. It's very interesting, right? And this is our goal, is to understand this conjecture. This remains open, but let me very quickly show you this. This is the same example we did before, and if you remember the computation, right, this we said was 6m11 plus m21, but that's the same, let me see if I can get this right, as 3e3 plus e21. So E3 is nothing but the sum of all square free monomials of degree 3. So we get 3 of these here. E21 is the product of two sums, the sum of all square free monomials of degree 2 and the sum of all square free monomials of degree 1, that is variables. So if I take the product of the sum of all degree 2 square free monomials times the sum of all the variables, well, if I want to get, let's say, x5 squared, x11, like I had before, I have to take x5 squared from here and x11 from here. On the other hand, if I want to get x3, x6, x7, well, I take 2 of them from here and 1 of them from here, and that's 3 more ways to get this. So this is an example, right? And the idea is if I take any one of these Hessenberg graphs and look at this chromatic symmetric function, right, then we're going to get a non-negative integer combination of elementary symmetric functions. So as I said, this is hard, it remains open, but we're trying to understand this. So Michel and I came up with a refined version of the Stanley-Stembridge conjecture, or if you prefer, a graded version. So what we're going to do is introduce another parameter. The other parameter for a coloring now, right, both the set of colors, which is the positive integers, and the set of vertices, they're both totally ordered in the natural way, right? And so we can take an edge. We know that the endpoints of an edge get distinct labels, and either these labels are ordered the same as the vertices of the edge or in the opposite way. And what we're going to do is count the number of, if you like, correctly ordered edges. Right, so here's an example. This is in fact a Hessenberg graph, and here's some particular coloring. Right, I used color 7 here, 11, 3, and 28. Now I look at each edge. This edge here has an ascent because 7 is less than 11. Right, this edge here does not, because 11 is not less than 3. This edge doesn't. This edge does. So in this particular, for this particular coloring, there are 2 ascents. Okay. So this ascent number is just a property of the coloring, a statistic associated to each coloring. And now you define the chromatic quasi-symmetric function. So for a general graph, this is no longer a symmetric function. You have the same generating function for colorings, except now you weight each coloring by the ascent number. And now if you go back and look, right, if I permute these colors in some way, I keep the set of colors the same, permute, this ascent number is going to change. So it's not the case that this power series now, right, it's again homogeneous in the x's, and it's got some, you can think of it as either a power series in the x's with coefficients in the polynomial ring, or a polynomial in T with coefficients in the power series ring, right? In any case, right, this in general is not symmetric, right? It just doesn't have to be, and it typically isn't. However, right, sometimes it is. And let's go back to the same example here and compute this thing. Right, so we have various kinds of colorings, right? Let's look at the number of ascents here. Here, there's 1 ascent. Now, you could ask what happens if the number used twice is bigger. There's again 1 ascent, right? I could use these colors like before. Here, there were 2 ascents, but I could permute this maybe this way. There's 1 ascent, and so on, right? But what you see is, first of all, this is some nice symmetry. It doesn't matter which monomial of the form xi squared xj. I usually have the same number of ascents. And what goes on here is what I'm really doing is counting ascents in a permutation. Right? I have all possible permutations of 3, 6, and 7. Right? And what I see is that I'm really getting an Eulerian polynomial. So what I get in this case looks like this: 1 plus 4t plus t squared m11 plus t m21, right? And actually, I prefer to write it as a polynomial in t. With coefficients, in fact, in the ring of symmetric functions in this case, right? So in this case, I don't like this thing in the way. Let me see if I can get it out of the way. I can, right? In this case, right, this is a symmetric function, if you like, with coefficients in the polynomial ring, or a polynomial whose coefficients are symmetric functions. And this is a theorem of Michel and myself. If I take a Hessenberg graph, right, I start with a Hessenberg function, I get a Hessenberg graph, I look at this quasi-symmetric function a priori. In fact, it's a symmetric function, and better than that, it's a sure positive symmetric function. So the sure basis for symmetric functions is an important and widely studied thing, right? And so the chromatic quasi-symmetric function of a Hessenberg graph is in fact a sure positive symmetric function. This is good news. What it means is associated to it is a representation of Sn, right, of symmetric group. The interesting part, I think, in fact, is that it's symmetric. The fact that it's sure positive is not surprising, because in fact it was known that symmetric functions of Hessenberg graphs were sure positive. So when t is 1, this is just Stanley's symmetric function, right? And Gesharov had proved shortly after Stanley introduced these symmetric functions that these things were sure positive when t is 1. So that's maybe not the surprising part. The interesting part is, in fact, that it's symmetric, right, when you have a Hessenberg graph. So then it's natural, right, to make the refined Stanley-Stembridge conjecture, which is that these things are in fact E positive. If I think of this as a polynomial in T with coefficients in the ring of symmetric functions, all these coefficients are again non-negative integer combinations of elementary symmetric functions. And just for our example before, we already calculated, right, what this looks like. This was M111 plus T 4M11 plus M21 plus T squared M111. And this is nothing but E3 plus T times E21 plus E3 plus T squared times E3. So this is the conjecture. And I mean, of course, this is a tiny little example, but one thing you'll notice is that this is a palindromic polynomial in T, right? Here's an E3, here's an E3. And we prove this, that these things are always palindromic as polynomials in T. They read the same this way as they do this way. And this is maybe some guess that this is a case, right, of we have sure positivity also, so there are representations, and the guess then can be that this is an instance of equivariant Poincare duality, if you like. There's some manifold whose cohomology admits a representation of Sn, and in fact, it's a very, very nice representation in the sense that the Poincare duality doesn't just hold for the dimensions of the cohomology groups, it holds for the representations. And in fact, this is what's true. So now comes some more technical stuff, right? So we take a Hessenberg vector. We have this Hessenberg vector. We already looked at this chromatic symmetric function, and now we take a generic element, a generic matrix. All this means, again, regular semi-simple means it's diagonalizable with n distinct eigenvalues. So if you like, you should just imagine it's diagonal with n distinct eigenvalues. What centralizes such a matrix? So I'm going to conjugate it by elements of GLNC, and I'm going to ask which centralize it. Well, if it's diagonal with n distinct eigenvalues, the only things that commute with it are all the diagonal matrices. They make a complex torus, right, of dimension n, although for our purposes really n minus 1, but never mind, right? So there's a torus that commutes with it, and anything that commutes with x is going to act on the associated Hessenberg variety, so that this is just something, you know, you could assign in an algebra class, right? I start with this condition that X maps the J space into the MJ space. And now I take some Y in this torus and I apply it to my flag. So now I see what happens to Y Vj, but they commute, right? X and Y. And therefore, since we have this condition, we also have this condition here. So it says if I take something in the Hessenberg variety and apply an element of the torus, I stay in the Hessenberg variety. So this Hessenberg variety admits a torus action. Right? This is the key point. This action is what's called equivariantly formal. This is a technical condition about some spectral sequence converging quickly that was introduced by Goreski, Kottwitz, and McPherson. I lack both the time and the expertise to give you a really good explanation of what this means. But in any case, this GKM theory applies. What does this GKM theory allow you to do? It allows you to determine both the torus equivariant cohomology and the ordinary cohomology instead of usually you get a presentation for cohomology, but here it allows you to get a representation. You can embed the cohomology ring inside or the equivariant cohomology ring anyhow, inside a product of polynomial rings using some kind of complex one skeleton, if you like, of this variety. So I just want to show you a picture. There's no time to give a really detailed explanation. You have this nice torus action. You look at the fixed points. In this particular case, the fixed points are indexed by permutation. So there's a graph, a so-called moment graph. Its vertices are the fixed points of the torus. Its edges are in fact the one-dimensional orbits of the torus, and these two fixed points bound a certain one-dimensional orbit, making a sphere, right? And if the orbit is one-dimensional, the stabilizer has codimension 1 in the torus, and therefore its Lie algebra is cut out from a vector space by a linear form. So each edge is labeled by a linear form, right? Each vertex corresponds to a fixed point, and what GKM theory says is that the equivariant cohomology ring anyhow can be represented inside a product of polynomial rings by assigning to each vertex a polynomial in these variables here, such that the difference of any two assignments across an edge is divisible by the edge label. So here's, right, I have these two. I've assigned this linear form here and this linear form here, and their difference is in fact T3 minus T1. It's divisible here. This difference divisible by this label, this difference divisible by this label, and so on. This is how you get cohomology classes. And now the key point is that we don't have an SN action on the manifold in general, but we do have an SN action on the cohomology ring, basically because SN both acts on this graph by multiplication and acts on these forms by permuting the indices. So if I take the transposition 1, 2 here and apply it, this is a cohomology class. Since these are linear, this lives in H2, you double, right? And if I apply this transposition 1, 2, what does it do? Well, it switches these two vertices, switches these two vertices, switches these two vertices. And so what I'm going to do is switch the labels. So I'm going to move this here and vice versa. I'm going to exchange these two and exchange these two, except I'm also going to act on these indices by the transposition 1, 2. So this T1 minus T2 here became this T2 minus T1 here. this T3 minus T2 here became this T3 minus T1 here. And now if you observe, these differences remain divisible by these edge labels. I didn't change the edge labels at all. They're still here, right? And so, for instance, this difference is T3 minus T2, which is divisible by this here, and so on and so on and so on. And this is the so-called dot representation, right? This gives an action of Sn on cohomology, right? I just want to gloss over the equivariant versus non-equivariant part. This is the dot representation. This was studied first by Giuliano Tomachko, right? So this is an example how the dot representation looks, right? So even though, as far as we know, this representation doesn't arise from an action on the manifold, right? But here it is. There's a dot representation, right? And now, as I said before, sure positive symmetric functions correspond to representations of symmetric groups. That's the Frobenius characteristic. This just assigns to each representation of Sn a degree n homogeneous symmetric function, which in fact is sure positive. It sends irreducible representations to sure functions. And this is a conjecture of Michel's and mine, which was proved by Patrick Brosnan and Tim Chow. A later proof was posted on the archive by Matthew Gay-Paquet. And what it says is basically what the only thing we should expect to be true given how the talk is going, which is that if I look at this dot representation and ask what symmetric function is assigned to it by the Frobenius characteristic, so it's a graded representation, right? We have every cohomology group here. We're considering them one at a time. We have this grading variable T. I have this dot representation. What Michel and I conjectured and Patrick and Tim proved was in fact that the Frobenius characteristic assigns to the dot representation the chromatic symmetric function. Well, not quite. Either over here you have to tensor with the alternating character, or in symmetric function language, you apply the involution omega, which exchanges the elementary symmetric functions with complete homogeneous symmetric functions. Right? And so what good is this? It changes the graded Stanley-Stembridge conjecture to a question about this representation arising in geometry. And if you've read Bruce's book or Richard's book, this is a restatement of the refined Stanley-Stembridge conjecture, right? It says that the dot representation of Sn, well, is an H positive symmetric function, or has H positive Frobenius characteristic. And if you know what H positivity means by reading Bruce's book, right, you know this arises from an action on a set in which each point stabilizer is a Young subgroup, a direct product of symmetric subgroups. Another way of saying this is that each of these cohomology groups has a permutation basis, has a basis that's permuted by Sn in this representation in such a way that the stabilizer of a basis vector is a Young subgroup. So when Michel and I came up with this conjecture, we thought that proving the conjecture, the Brosnan-Chow theorem, would be the hard part, which is correct. And we thought that then proving the Stanley-Stembridge conjecture would be easier, which so far is incorrect. The Stanley-Stembridge conjecture remains open. The goal was to introduce this geometry, right? And that this would make proving this combinatorial conjecture of Stanley and Stembridge easier, right? That turns out so far not to be the case. So I hope no one in the audience is about to be cheated. I just want to mention some recent progress towards the Stanley-Stembridge conjecture. So this is not so recent. The first thing that I should tell you is, in fact, well, Michel and I came up with this conjecture on our own, but Clearman, Hyatt, Shelton, Scandaris showed that, in fact, I mean, this is not trivial. They related the chromatic symmetric function to Heck algebra, type A Heck algebra characters. It turns out that this refined Stanley-Stembridge conjecture is, in fact, a special case of a conjecture of Heyman. So there's some close relation with Heck algebra representations and this whole story. we were hoping to get combinatorialists and geometers interested in geometry, and our initial efforts were sort of have the opposite effect. We got some geometers interested in combinatorics. So with clever combinatorial manipulations, Sujin Cho and Jisun He, Martha Prekup and Megumi Harada showed that the refined Stanley-Sembridge conjecture holds when the Hessenberg graph has independence number 2. It's got lots of edges. What's considerably harder, but still doable by Sujin Cho and Jae-Hyun Hong, is that you can do this with independence number 3 also. This is not so easy. So these are sort of progress, but by force. But now there are recent preprints, again, Sujin Cho, Jae-Hyun Hong, and Yunjung Lee, who've identified certain cohomology classes of the Hessenberg varieties and conjectured, in fact, that these classes generate the desired permutation modules. So to my mind, this is the first serious progress at realizing the dream that Michelle and I had to settle this conjecture of John and Richard using geometry. There's a long way to go. What they're able to prove so far using these ideas are things that can be proved using direct combinatorial methods. But still, this is very interesting. And there, I think, are 2 preprints on the archive where you can see how they're thinking. Let me maybe mention one more thing, which is that Stembridge's original immanent conjectures, in order to prove the one at which the Stanley-Sembridge conjecture is aimed, you need to prove not only the Stanley-Sembridge conjecture, but another auxiliary conjecture, which says that a certain class of symmetric functions are all non-negative integer sums of chromatic symmetric functions. There's some yet to be published progress towards that by Nate Lesnevich, who's a student working with Martha and myself. So that's the story, and I hope I have not gone way too fast, because I used way less time than I did on this when I gave the practice talk. And so happily for me anyhow, that gives me a chance to talk a little bit more about my work with Laura and Martha. Let me just pause for a second and maybe give Bruce a chance to get a word in edgewise if there are questions I can answer now.
There were no questions in the chat yet, so go for it, and we'll have more questions. We'll have some questions at the end, hopefully.
Great, thanks very much. So the general kind of question that Martha, Laura, and I, and we're certainly not the only ones, are trying to attack are, what do these Hessenberg varieties look like? Right. So the regular semi-simple ones, I should say that they are always smooth. In general, these Hessenberg varieties are not smooth. The other thing I should say is that the definition I've been using, which was given by Damari and Shaman in their work on applied mathematics, so these are called Hessenberg varieties because if your Hessenberg vector is 2, 3, 4, 5, n minus 1, n, right? What you're really asking is, in fact, if you use the coset model for the flag variety instead of the flag model, you're asking which matrices conjugate your matrix X in the Hessenberg form, right? And so this is Hessenberg form is something that's of use in numerical linear algebra. And it turns out that the topology of these Hessenberg varieties controls the speed at which certain algorithms can move things into Hessenberg form. So this is a very beautiful thing. There are more general definitions of Hessenberg varieties. We just looked at the type A Hessenberg varieties. For every reductive group, there's a class of Hessenberg varieties. These were studied by Damari, Procesi, and Shaman, at least when X is again generic, regular, semi-simple. In fact, there's more general class. You can look at representations of reductive groups and subspaces invariant under parabolic subgroups and define Hessenberg varieties. So we're just looking at a corner. And the question we're trying to attack now is, what do these things look like? Right? So it's a result of Juliana Tomachko in type A and Martha Prekup in arbitrary type, that these admit affine pavings. This means the cohomology is concentrated in even degree, and that's already a huge restriction. And so one thing we tried to study was, well, this question was in fact raised by Juliana, Schubert varieties, right? Orbits of the Borel subgroup on the flag variety also have cohomology concentrated in even degrees. And we asked ourselves, well, or Juliana asked us, which Schubert varieties are Hessenberg varieties? If you look at small n, most of them are. Right? And the question was, are most of them always Hessenberg varieties? And in fact, that's not true. So we have a pattern avoidance necessary condition. So I take a Schubert variety that's associated with a permutation. It turns out if that Schubert variety can be realized as a Hessenberg variety, then W must avoid one of the two patterns that are required for XW to be smooth. Right? This says immediately that in the long run, a vanishing proportion of Hessenberg varieties are Schubert varieties by the Stanley-Wilf conjecture or the Marcus-Tardis theorem, which says this means exponentially many Schubert varieties are Hessenberg varieties, so vanishingly many out of n factorial Schubert varieties are Hessenberg varieties. On the other hand, the situation is not as pleasant as it is sometimes. There's not a necessary and sufficient pattern avoidance criterion for a Schubert variety to be a Hessenberg variety. Okay. Here are some more results we have. So I think this top one is unsurprising, but useful and interesting. So one thing you might notice, I said it repeatedly, it didn't matter what the eigenvalues were in the examples we had. So if I take a regular semi-simple Hessenberg variety, I'm just interested in the cohomology. It doesn't matter which n eigenvalues I choose. They all have the same cohomology. That was, implicit in what we discussed. It's open whether they're all isomorphic as algebraic varieties. They are all homeomorphic. But the key point, if we're interested in things like Poincare polynomials, Betti numbers, I might as well assume that all the eigenvalues are integers. Right? The actual eigenvalues, even in a non-semi-simple case, don't matter. It's just how, the multiplicities of the eigenvalues and the Jordan type matters, right? So we might as well assume that we have an integer matrix with integer eigenvalues, and then we can reduce the matrix mod P and just ask how many FP points are there on the associated Hessenberg variety. You can define a Hessenberg variety over FP in the same way. And it turns out if you take large enough P, if I start with an integer matrix, say in Jordan form, I take large enough P and I count the points, turns out it's a polynomial point count. And what polynomial? Well, essentially the Poincare polynomial, except since the cohomology is concentrated in even degrees, I have to use the square root of P instead of P, right? So this turns out to be useful because, well, there are these affine pavings that give you the Poincare polynomial, but the conditions given by Juliana and Martha are somewhat complicated, whereas in many cases, just counting how many FP points there are on a Hessenberg variety is less difficult. Right? So we can get Poincare polynomials. We use this to study Hessenberg varieties of codimension 1 in the flag variety. You have to start somewhere. There are not general theorems on these things, or very few, so you have to start somewhere. We studied Hessenberg varieties of codimension 1 in the flag variety under a slightly more general definition than the one I've given you. And it turns out you can characterize those, well, if X has an eigenvalue of multiplicity n minus 1, then you can have codimension 1 for various Hessenberg vectors. But in general, what you need is sort of something that almost looks like the whole flag variety. There's only one condition. So we studied these things for arbitrary X, and here's a sample theorem that we were able to prove. If I take a nilpotent matrix X, we can determine the entire singular locus of this codimension 1 Hessenberg variety. It's another Hessenberg variety. This, I think, is interesting, right? I just have to change the Hessenberg vector. So the singular locus of a codimension 1 nilpotent Hessenberg variety is just another Hessenberg variety for the same matrix. We have various other results around these. We have a complete characterization of which codimension 1 Schubert varieties are Hessenberg varieties, very few of them, and various other theorems of this nature. I think there's lots of interesting stuff to be found here, and we're still at it. There's one preprint on the archive and another one on the way. So I was sure I would run over time, and I'm actually happy to have run under time. And let me thank the organizers very much again, and thank all of you for listening. Thanks a lot.
Okay, let's thank John for a very interesting talk. And we have tons of, yes, exactly. If you want to unmute and clap, that's always appreciated. Because it's still strange giving talks in this Zoom world where you don't have much contact with the audience. So we've got tons of time for questions. You can either put questions in the chat, or if you want, use your raise hand function, and the floor is open. Well, I had one question to at least start out. So, one of the ways to attack the Stanley-Stembridge conjecture is to put a fixed ordering on the vertices and then look at the corresponding generating function in non-commuting variables and study its properties. And then, of course, you can let things commute to try and get what you're actually after. Has there been any attempt to try and do that using ascents and or trying to associate some sort of Hessenberg-like variety to these?
Not that I know of, no. And this is a very good question and something to think about. But no, I know of no such efforts. I could be ignorant, but I don't know anything.
I don't think you're ignorant, John.
Well, about this and many other things.
Right, exactly. Let's see, there's a question from Joel Lewis, which he calls silly, but no questions are silly in my book. He says, you talked near the end about taking things mod p. Is there any reason to restrict to prime fields rather than prime powers, right? A general Galois field.
No, it will still be true. It'll be a polynomial in the you can take any field you want, and the Poincare polynomial of the complex Hessenberg variety will be a polynomial, will be obtained by counting the points over any finite field. I should remark that Patrick Brozin and I have a conjecture that point counting over finite fields, there the eigenvalues do matter, right? If I want to count the rational points, right, and I have some matrix over a finite field, so let's say it's generic, so it's diagonalizable over the algebraic closure. In the language that I'm using in this talk, the conjecture says that the chromatic symmetric function, if you expand it in the power sum basis, tells you how to count points over a finite field where the permutation indexing the particular power sum that you're talking about, or character value, if you like, tells you the degrees of the irreducible factors of the characteristic polynomial over the given finite field. Or if you can phrase this in terms of the Weil conjectures, and it says something like the eigenvalues of an SN element of type lambda are determined by the eigenvalues of the Frobenius map on a variety if you use X to be sort of type lambda in the sense of its irreducible factors of its characteristic polynomial. So I think there are some very interesting things going on with arbitrary finite fields, but we don't know them yet. Patrick says he can prove the conjecture, and I believe him, but we don't have a paper yet.
Okay, let's see. Another question in the chat, this one from Franco Saliola, which is there a known analog of Schubert polynomials for arbitrary Hessenberg varieties?
There are many people who could answer this much better than I can, and therefore I am reluctant. I saw that Laura is here. I don't know if Martha's here. So I don't think I'm answering Franco's question very well. What I can say is there is recent work of Vasu Tiwari and Philippe Nadeau on expressing the classes of Hessenberg varieties in the flag variety in terms of the Schubert polynomials. I don't know if that really addresses Franco's question or not.
I think indirectly it does, at least. I mean, this is something I didn't know of already, so thank you.
Thanks.
Another question from Francois Bergeron. Although this needs clarification, have you thought about diagonal versions of these questions? By which he means this would be like passing from the cohomology ring of the flag variety to the diagonal coinvariant ring.
I know nothing about this. This is another good question which I cannot answer at all.
Okay. Other questions?
Maybe I should just make a comment that Megumi Arara told me that she has some ideas about Franco's question about Schubert polynomial for arbitrary Hessenberg variety. So you should talk to her.
Thanks.
Excellent. Excellent.
Thank you.
The collective wisdom does it again. Other questions or answers?
What about other statistics than ascents, let's say major index, or is something also coherent with the chromatic symmetric functions?
That again, I really don't know. I should say that the way we discovered this conjecture in the first place was when we found how to find the joint distribution of the major index and the exceedance statistic, essentially using the chromatic symmetric function of the path, right? And so the way we have it set up, there's a different pair. I don't know if Michelle's here, she can remind me, of Eulerian and Mahonian statistics that are sort of directly enumerated using principal specialization of chromatic symmetric function of the path. And it turns out this is equidistributed with Maj and X. And this is how we, in fact, discovered this whole thing, by trying to figure out what was going on with that. So again, I think I'm not directly answering your question, but I would not be surprised if there are interesting things about permutation statistics yet to be discovered using these kind of geometric objects, but I don't know what they are.
Thank you.
Thanks.
Any other questions? Okay, well, give us all then a little bit of time for a break, and let's thank John one last time for a great talk.
Thank you all very much. Let me
Yes.
unshare and mute myself.